Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Thank you for joining us today, and welcome to this AI for Good session on the AI for Fusion Energy Challenge. Many thanks to our speakers, Dr. Christina Rea, research scientist at the Massachusetts Institute of Technology, and Dr. Wei Zhang, associate professor at the Huazhong University of Science and Technology, for accepting our invitation. The International Atomic Energy Agency is a world center for cooperation in the nuclear field and seeks to promote the peaceful uses and applications of nuclear technology. This AI for Good session will provide an overview of the AI for Fusion Energy Challenge, which aims to explore the potential of machine learning in contributing to multi-machine disruption prediction. Please type your questions and comments into the neural network chat function. We'll try to address them during the session. For those of you working or interested in fusion and plasma science, make sure to check out the IAEA's AI for Fusion platform. The link will be shared in the chat. Our Coordinated Research Project on Artificial Intelligence for Accelerating Fusion R&D is developing AI applications in fusion science at an international level, such as this challenge. Please consider attending our next workshop on AI for Accelerating Fusion and Plasma Science from November 28th to December 1st in Vienna, Austria. The links are in the chat as well. Without further ado, please welcome Dr. Christina Rea and Dr. Wei Zhang.
Hello, everyone. Hi, Decker. Thank you for the kind introduction. Let me just set up my screen sharing. All right. So thank you, everyone, and thank you for giving me the opportunity of clarifying some, of presenting this AI for Fusion Energy Challenge. And Decker has already provided like a great brief introduction to it. So I'm going to go a bit more into the detail before heading there. I just wanted to thank really all the contributors that were allowed us to make this data challenge something real. In summary, the MIT Plasma Science and Fusion Center and the Huazhong University of Science and Technology and the Southwestern Institute of Plasma Physics worked under the IAEA Coordinated Project on AI for Fusion that Decker mentioned to share data and workflows for data analysis for this multi-machine disruption prediction challenge for fusion energy. The data that we selected comes from magnetic fusion experiments like named Alcator C-Mod, JTEXT, and HL2A. Some still in operations, some like Alcator C-Mod stopped operating in 2016, but still present like an immense data repository useful for generations to come. ITU has led the organization of this data challenge, which is now hosted by the Zindi platform. And you can find it at this link that maybe I can ask Yaher to drop it in the chat as well. The ITU has been hosting and sponsoring AI and ML challenges under 5 thematic areas. They've been sponsoring areas of machine learning and 5G challenges. We are just now joining the portfolio of offerings that ITU sponsors, and with the AI for Fusion Energy Challenge. But then we also have geospatial analysis as well as climate change more broadly. The ITU has been sponsoring data challenges since 2020, with more than 4,000 participants, 56 open challenges involving participants from more than 100 countries worldwide. typically, yes, this is another examples of how we can solve challenges in AI and machine learning, for example, using communication networks. This is for the 5G challenges. And then, as we were mentioning, other geospatial and SDG-related problem statements, the Sustainable Development Goals of the UN nations. The goal of sponsoring such challenges is really to create a community of value, to provide practical solutions through AI and machine learning techniques, to allow students and professionals to compete, as well as interact with experts through such webinars or just joining the competitions themselves, to create roundtables and hands-on sessions, so bridging the gap between communities, as well as creating mentorship opportunities. The ITU framework maps onto the Coordinated Research Project, AI for Fusion, and is specifically on the work packages number 1 and number 4. That sounds a bit like secretly named, but they are centered around the magnetic fusion energy, data, and community, here highlighted in red. And the work package 4 is really centered around community engagement and workforce development. The Zindi Data Challenge will indeed broaden participation to fusion open questions, in particular by leveraging MFE data, and around the problem of disruption prediction and characterization. The data that we are using, as I was mentioning before, comes from the Alcator C-Mod, JTAGs, and HL2A tokamak devices through these participating institutions. We opened the challenge now late September, I believe, a few weeks ago, and we will keep it open up until mid-November 2023. After that, we are going through an evaluation phase, and then we will assign awards in December 2023. Now, to go a bit more into the problem and to give a bit of background for those of you who might decide to join the challenge or have joined the challenge, but not necessarily are fusion experts, I'll be providing a few introductory slides and a few introductory concepts to fusion. So fusion research is tackling transformational technologies to provide alternative carbon-free electricity generation. So we are trying to reproduce the reactions that basically power our stars, like the sun, just on through laboratory experiments. And the laboratory research is conducted via either the heating and confinement of a plasma of hydrogen isotopes via magnetic fields. This is what we call magnetic confinement fusion, what we refer to as an acronym to MFE, magnetic fusion experiments, or magnetic fusion energy. And ITER here, under construction in France, is one of the examples of such devices that we will be developing in order to get to fusion energy production. The other approach is through inertial confinement fusion or inertial fusion energy. And this approach entails the heating and compressing of the fuel target, of a solid fuel target, via highly energetic lasers. And the target is, of course, composed by hydrogen isotopes, here represented in this capsule. And these are all the laser beams, basically, that heat the target. And this is the approach that the NIF, for example, the National Ignition Facility here in the US, is leveraging and is using, and that has recently produced the ignition results just last year. However, my background is in MFE plasmas, so I'm a bit biased, so we will take a closer look to MFE plasmas. The overall qualitative statement that we can actually put out there is that in general, fusion plasmas are characterized by nonlinear phenomena that make them really, really hot or really, really fast. These plasmas are hard to diagnose. We have lots of theory and experimental data. It's not so easy to bridge the two environments, basically. Just to give you an example of all the different time scales and spatial scales that affect fusion plasmas, here on the top, I'm showing some of these time scales mapped onto characteristic plasma events and instabilities that might arise. And here at the bottom, you can see also the spatial scales that are involved, which span several orders of magnitude. And so it is really challenging to develop first principle solutions. However, we have many experimental devices out there that are operating or that have operated in the past. So we have a wealth of a huge amount of experimental and simulation data that is available. And this has enabled so far several typologies of machine learning applications, several types of machine learning applications, from the optimization of experimental design to trajectory planning and optimization to the design of fast surrogate models to accelerate simulations that might otherwise take hours of compute time, days of compute time. What we'll be talking about today is really about the monitoring of the proximity to instability. And in particular, disruptions. Disruptions are still like a challenge, to our path to burning plasma solutions. Major disruptions occur when we basically have a final loss of control, and those evolves on timescales of milliseconds. We have a fast drop of the plasma current, which leads to the loss of the confinement of the plasma itself. This fast transient causes large induced voltages and currents with rapid thermal losses that cause surface damage. What does it look like in actual time traces is shown here with a screenshot from an Alcator C-Mod plasma discharge. On the top panel, you have the plasma current, and here we have the sudden loss of the plasma current, causing in turn the loss of the confining podal field. We call this current quench. And here at the bottom, you can see the time trace of the temperature of the plasma in the core that drops quite a few milliseconds before or microseconds before the current quench itself. I mentioned that the rapid thermal loss can cause surface damage, but also the uncontrolled termination of the plasma can cause the acceleration of electrons and particles. And this can localize and form a runaway electron beam that can eventually hit the first wall. And this is a view of basically the Alcator C-Mod tokamak chamber. And you can see that when this beam hits the wall, basically what happens is a sputtering, so erosion of the material of the first wall, and a consequent melting that can happen afterwards. So what should we do with disruptions? In current experimental devices, we typically accept the damage and continue running experiments to explore the physics and the physics boundaries. When the energy is involved and the unmitigated consequences are hard to tolerate, we typically inject massive gas quantities or shattered pellet in order to really help mitigate the damage of uncontrolled terminations. But we would really like to go, the solutions that we would really like to adopt is to avoid such disruptions, such disruptive events altogether by detecting precursors, and therefore steer the plasma away from the disruptive boundary. Keep it under controllable boundary. However, the community has done several statistical studies in the field, and we have identified complex chain of events. You're not supposed to basically digest this diagram, this complex diagram here on the left, but this is to show you all the possible disruptive chain of events that characterize the plasma disruption dynamics on a particular experimental device that is called JET, which has now run across its 40 years of operation and will soon shut down at the end of the year. The width of the connecting arrows is in turn related to the frequency of the event occurrence. All these boxes indicate different plasma dynamics events or hardware failures that might arise. And the issue here is that this diagram was taken out of a intense study of over 10 years of operations at JET, but similar statistical studies are not always available across different tokamaks. We can still rely on a wealth of experimental data in order to enable machine learning application. And the idea and the hope is that by adopting those solutions, we can timely identify precursor phases that can allow then the plasma control system to take proper action and steer the plasma away from disruptive boundaries. The challenge of disruption prediction will be even greater for next generation devices for which we don't have yet any data and for which the operational space will be quite different with respect to the current machines. So there is an outstanding question, and is how to use the existing tokamaks data to build a model that can work on future reactors. And techniques borrowed from the machine learning community can hopefully help address that. Here I'm mentioning the domain adaptation and transfer learning techniques. These allow black box systems, so machine learning systems, to overcome biased data sets and generalize knowledge across different tasks. In particular, domain adaptation aims at learning the same task under differently distributed source and target domains, while transfer learning aims at learning to perform new tasks on a limited target domain given knowledge gained on a source domain. Multi-machine disruption prediction is seen as a test case for domain adaptation and transfer learning techniques, provided that we have enough data to properly map source and target domains. The idea is to similarly train a model with as much tokamaks data as possible and hope that some miracles of large data will happen. This requires indeed a large fusion database. It requires collaboration. And this multi-machine disruption prediction data challenge is exactly an example of that. Let me go a bit more into the details of the problem setting, the problem statement. So we have data from many different experimental devices. I was mentioning Alcator C-Mod, the JTEX. These are intrinsically different devices that do represent the best test case for potential domain adaptation and transfer learning solutions or design of solutions. JTEX is, for example, a circular tokamak, while Alcator C-Mod runs in this particular diverted configuration. So this D-shaped configuration, which was empirically found to get you to best optimized performances. The three teams involved in this data challenge competition have spent a long time designing and selecting the features of interest, so the plasma signals that would be shared as part of the challenge. Our focus has been on raw data from both Alcator C-Mod, JTEX, and HL2A. And then we have complemented this with a few extracted features. We call it extracted, or I would say slightly derived features that come, for example, might come from equilibrium reconstruction codes or other approximations. This is a screenshot of one of the documents that are complementing the data challenge material available on Zindi. We have data, for example, from many different diagnostics. So this implies a multimodal data source. And we have selected different sampling rate in order to preserve and maximize the information that is carried by these features and these signals. We are including things like plasma current, toroidal magnetic field, information about the displacement of the plasma in the chamber, information about the density of the plasma, and then raw data from many different channels. For example, what we call AXUV, which looks at the radiated power from the measurement for radiation emission from the plasma, for example. But we also have soft X-ray data, Mirnov probes, and this data is also sampled at higher sampling rate at 5 kilohertz. We settled on a total number of 100 features. The requirement was that the raw channels that we were extracting from similar diagnostics across different devices would cover the same plasma regions, mostly looking at the core of the plasma and at the Q-core1 and Q-core2 surface that we know carry a particular information from the point of view of the stability of the plasma. And we have picked a similar ratio between different diagnostics types, not to bias the information that is available across the different machines. And as I was mentioning, we have settled on a consistent sampling rate across the different machines, with high sampling rate that is around 5 kilohertz and the remaining one at 1 kilohertz. Regarding the supplemental material that we have available on Zindi, there is a simple introduction of what a disruption is and why disruption prediction is important. And I'm sure that this webinar, the recording, can also be considered as part of supplemental material. And then we also have available example notebooks, and Zhengwei will provide a quick demo or show some details of that, where we can see step-by-step instructions on how to build and evaluate a disruption predictor. The demo code is available on this GitHub repository. And then we have also some other sample preprocessing notebooks focused on reading data, normalize the signals, extract sample features, etc., and evaluate, and also for evaluation of the model itself. The example submission material will be some example submission material will be requested to the top 10 teams that around the end of the competition will be selected, and we will require that the top 10 teams will provide a README, a markdown file that is covering how to set up the folders, where each file is saved, how the order in which to run the code, so clear instruction on how to run the code, explanations on how the features were used or which type of features were used, the environment for the code to be run, whether it's we need some configuration file in the case, the hardware that is needed, whether it was like a Google Colab environment or specifications of the local machine that was run on, and the expected runtime for each notebook. One strict requirement is that the code needs to be open source and that run properly with not necessarily debugging of it. Okay, I went too fast. One highlight that I wanted to provide is that the JTAGS disruption database software library was used to retrieve the data across the 3 different machines. Again, an example of a collaborative use of an open source software library developed by the HAST team. This is available on GitHub. It's fully open source with an MIT license and available with documentations and examples. And also a demo with metadata and file of repository of 20 JTAGS shots is also available independently of the data provided with the challenge. And the HAST team also manages a Discord server for questions about specifically the JDDB. This might be useful to participants in the competition. I know that Zindi has also a platform for a forum on discussions related to the competition, but this allows you to address also the direct software developers. I'm leaving out here a typical workflow for extracting data using the JDDB software library, and how this basically produces a set of metadata files as well as data files that can be then used for the training inference of machine learning models. Okay, so in conclusion, I wanted to mention that I wanted to highlight that the PSFC, HAST, and SWEEP teams have collaborated under the IAEA Coordinated Research Project AI for Fusion. The ITU has coordinated the realization of such data challenge to broaden participation to Fusion. And the data challenge is now open and hosted on Zindi. And for further information, I'm leaving here the contacts from Professor Zhengwei and myself. With that, I will leave the floor to Professor Zhengwei and mute myself. Thank you.
Hello everyone, and thank you, Christina, for the introduction. And I'm going to show you something about how we do disruption predictions from a machine learning perspective. Okay, I believe most of the contestants are not from the Fusion community, so they are not quite familiar about what is disruption and disruption predictions. So I will share my screen here and try to go through this document. I guess this document is included in the repository, the example repository. So it has some instructions about what is disruptions, and I will try to explain some of that to you. And first, this is so let me see how to. Okay, the data you have on your hand is a lot of HDF5 files. They are each file is unshorted in fusion experiment is an experiment. So in one shot we have a lot of time series data, so this is just some example of it. So one of the most important one, I guess, is the IP signal. This signal is it shows the plasma current. So what is a disruption? Disruption is a quick the plasma current just drops really quickly, in below 10 milliseconds on JTAGS. So you can recognize disruption with your eye very easily on this picture. But what is disruption predictions? So you have to predict disruption before disruption happens. So at this time disruption happens. So you inference, your model will inference on each time step. You can use all the data before this time step. Let's say you are at this time, so you can use all the data before and to predict whether disruption will happen 10 or 20 or 50 milliseconds after. If the model thinks the disruption will happen, it will raise the alarm. The alarm will trigger the disruption mitigation system, and that would protect the machine. So let's see here. So this is a zoomed in image of that time series. This is the IP signal, and the red line here indicates the disruption. So disruption happened here. So you can see those are all the diagnostics, not all, some of the diagnostic signals in the experiment. So you don't really have to understand what the physical meaning of these signals, like the NE is the density, the SRX is the soft X-ray radiation, and this is another kind of radiation. So you don't really have to understand this, but it's just different measurement of the plasma. So you can see before the plasma disruptions, the signals looks different here. But you can see we only have like less than 5 milliseconds before the disruption, when you can see obvious change in the signals. So if you detect disruption or predict disruptions at this time, you won't have enough time to trigger the mitigation system. The disruption mitigation system would take like for Italy, it would like take at least 30 milliseconds to take effect. So on JTAGS, it takes much less time because JTAGS is much smaller. So you need to like at this time you have to like predict the disruption will happen. So how do we do that? So from machine learning perspective, we label the time series with different labels. Here, the red part, we call it the precursor. So basically, you are trying to make a time series classification model, which classifies the normal signals. So at this time, disruption will not happen anytime soon. So the other label is a precursor. So when you recognize the precursor, it means disruption is coming. So you raise the alarm. So the first step is to label the time step. Label the time series. This red part here is like this is like 10 milliseconds before disruption. This is for JTAGS. For C-Mod, I guess it's like 40 milliseconds. Why it's 40 milliseconds? Because we think, you may expand this red part more than 40 milliseconds, because the standard we are try to classify the correct prediction or not correct one is you have to predict the disruption before 40 milliseconds before the disruption happens. So you need to like raise the alarm 40 milliseconds before the disruption happens. Okay, so I think that's pretty much it. And let's see what I have missed. Okay, there are like more than 100 diagnostics in the provided HDR files. So you don't have to use all of them, but the more data, the better, maybe. And you can extract some features from those signals. You don't have to use the raw signals because the raw signals sometimes is very high dimension, so it will pose challenges on the training of the model. And let's see, anything else? Oh, here, this blue line is the raw signal. The orange line, the orange line is the extracted features. Those features are extracted with plasma physics knowledge. So if you don't know tokamaks or plasma physics, you may not extract such features, but you can extract general time series features like the frequency, the amplitude. You can use those kind of techniques that's in time series classification. You can use that technique to extract features. Okay. One more thing is that the evaluation, how we evaluate the result. So we evaluate the result on shot. So you predict whether this shot is an disruption or not. But you have to you don't have access of the whole shot. You have to do it step by step in time series. And when you found the precursor, you raise the alarm. And when you raise the alarm, this shot will be predicted as disruptions. So about the data, I guess let me quickly show you the data. This is the data from JTAGS, and I guess you have 3 data sets: one JTAGS, one HR2A, one C-Mod. So JTAGS and HR2A are used as the existing tokamak. So you have hundreds of shots from them, and all of them has metadata about whether it's a disruption or not, and when the disruption happened. And for C-Mod data, you only have like 10 or 20 maybe data with the labels. So you know they are disruption or not. But the rest of the C-Mod data does not have the labels. So you don't know the whether it's a disruption or not. And the data, oh no. And the data we gave you only contains the flat top part. So not the ramp up, not the ramp down, only the flat top part. So if we don't tell you it's a disruption or not, you cannot simply recognize it's a disruption shot or normal shot from the IP signal, because the ramp down part is clipped away. You don't have that data. And for the evaluation data, the data is not cut here. If it's a disruption, it is cut like 40 seconds before the disruption. So 40 seconds within the disruption is not included in the data. So as long as you can raise the alarm anytime in that time series, you are considered those are considered successful predictions. Okay, I think that's it. The evaluation is quite simple. It's just a binary classification task. So you can evaluate it with all the like confusion matrix or true positive and false positive rate. You can evaluate your model with that. But remember, the evaluation is on shot, not on time steps, So your model inference on time steps, and when it raises alarm, it labels the shot as disruption, and we evaluate that result on shot. So I don't know if I made myself clear. Okay, I guess so. Let me address some discussions on the Cindy discuss. Okay, here. So, do we have to use JDDB based processes to process the data? So the answer is no. You don't have to use the base processors. The processors, if you are not quite familiar of how to make a processor, you can skip the processor part. You just use JDDB to get the time series data out of the HDF5, or you can forget about the JDDB if you are familiar with HDF5 files. You can do it yourself. So the basic processor module error. I guess the code we have in our example repository is working, will work. We have tested that, but I'm not sure why this error happens. But you can skip on the processors. I said you can skip on the processor. You can process the data by yourself. So help loading the data into the Jupyter Notebook. So it's just HDF5 files. If you are familiar with HDF5 files, you can do it yourself. And if you are using JDDB to load the files, here is a document of JDDB. And in this repository of JDDB, we have documentations about how to install it and how to use it. So reading the data is quite simple. The complex part, you can just ignore that. And what's next? What's that? The baseline code. Yes, the baseline code you can find in this repository. We have the baseline code, and I don't think we have time to go through that. The baseline code has two notebooks. One is called a free main processing. Okay, this file is about how to extract features from the time series signals. So you can completely ignore that because you can extract features yourself, or you just use the raw data. And the other notebook is the model training and eval notebook. So this is about how to train the model. It is very simple because it's just a time series classification prediction. So I don't know if it has. We don't have time to go through that, but you can read through that. I think this code is not quite complex. This code is using the JDDB file repo to read the HDF5 files and nothing more. The performance package, you can completely ignore that. This is used to help you evaluate your results, but you can evaluate it yourself, of course. And the model itself was built with like GBM algorithm, and you pretty much just need all this to build a model. It's quite simple. So the biggest difference from like speech recognition or an image recognition, image classification, is that you inference on time steps, but you label the shot. You label the whole shot. So one more technique is that if you at some time step your model raised an alarm, it doesn't necessarily mean disruption will happen, because the signals may have some noise and it may trigger the alarm. And so you can wait for a few alarms in a row and then raise the alarm for this shot. So this will address the noisy issue. Okay. Anything? I think I have finished my talk, and if you have questions, you can post it. Okay, thank you. I will mute myself.
Great, thank you so much. If you have any questions, please type them in the neural network chat function. There have been already a couple of questions regarding the material. So the majority of the material will be available on the Zindi link that is already in the chat. Also, the slides will be available, and the GitHub is also in the chat already. I have a question for Christina. What do you and the team expect from this competition?
Great question. I think the main goal is really to just broaden participation to fusion challenges. We don't expect to solve disruptions. We do expect to just, a broader communication across different communities, and just to reach out to those communities who might not know about fusion challenges, or, you'll never know what great solutions may come out of simple problems and addressing simple problems. So I think any lessons learned would be very beneficial also to port back in our community.
Great, thank you. And another question for both of you. Do you have any advice? What should participants do to win? Are there any specific tips that you'd like to share?
I'll let Zhengwei answer that.
So the data we have provided, I think the sad thing about it is not, I don't think it would support a very good model. So my suggestion is to keep it simple, and try if it works. I think keep it simple. Just build basic models. I think.
Great, thank you. So if there are no further questions, we will end it here. Thank you everyone for joining us, and thank you to our speakers, and good luck for a challenge.
Thank you for moderating, Viajer. Thank you, everyone. Good luck.
Thank you, everyone. Good luck. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Mm-hmm.